Hello everyone, welcome to the third video lecture of this series. Today we are going to discuss the binary number system, addition and the subtraction. It will be a three-part video, and in the first part we are going to discuss about the binary number system, decimal to binary conversion, binary to decimal conversion, binary coded decimal numbers or the BCD numbers. Then we are going to discuss about the octal and the hexadecimal number system. Now let us see what is a binary number. A binary number system uses base 2. So it can have either 0 or 1 value in one digit. A binary digit is called a bit. So bit can have 0 and 1 value. Now for any number system, if the base is b and there are total d digits, so the total number possible is b to the power d. Now consider we are discussing about decimal number. So decimal number, the base, that is b, is 10 and we are taking 2 digits. So total number is possible 10 to the power 2, that is b to the power d equals to 100, right? And what are those 100 numbers? 0 to 99. So the last number will be b to the power d minus 1. So in case of binary number, the base is equals to 2. Now if we are considering there are 3 binary digit or bit, so the total number possible will be 2 to the power 3, that is 8. And what are those numbers will be 0 to 7. 7 is what? 2 to the power 3 minus 1, right? So by a 4-bit binary number, it will be 2 to the power 4, that is total 16 different number will be possible, and the range will be 0 to 15. Okay?
In binary number system, a series of 8-bit or a number represented by 8-bit is called 1 byte. So 8-bit number or 1 byte number can generate 256 total number, that is 0 to 255.
Here we are discussing only about the positive numbers, not about the negative numbers. So these are positive integer numbers 0 to 255. A digital computer understands only the binary number system, and in binary number system the value 1 and the 0. In computer it will be represented by high voltage and the low voltage. So the next is conversion of decimal number into its equivalent binary form. We human understand only the decimal numbers. So let us take 127 in decimal, that we understand. But a computer does not understand what is a decimal number. It only understands the binary numbers. So we need computer need to convert this into its equivalent binary form. So how it will be done? It will be done using the quotient and the remainder method. What is the quotient and remainder method? The base is here 2. So 127 is the decimal number. We have to divide that by the base of the number system, while in case of binary it is 2. So what we will get? We will get a quotient of 63 and the remainder is 1. Repeat this division process until and unless we get a quotient which is less than base. In this case it is base is 2, so the quotient until and unless we get a quotient 1, we are going to continue this process, right? So 63 divided by 2, the quotient will be 31 and the remainder will be 1, like this. 15 and 1, 7 and 1, 3 and 1, 5 binary 1 and 1. This is called the most significant bit. This is the leftmost bit. Now, this bit is called the least significant bit, and this is the rightmost bit. Right? Now, after this, we have to take a bottom-up approach. So, the most significant bit will be at the leftmost position. From there, we have to go to the top. So, the number will be 1, 1, 1, 1, 1, 1, 1. So, 127 is binary equivalent will be 1, 1, 1, 1, 1, 1, 1 in binary. Right? Now, take another example. Suppose the decimal number is 152. So, 152 modulus 2 will give me 76, remainder will be 0, 76 is 38, remainder 0, 38 is 19, remainder 0, 19 modulus 2 will give me 9 as a quotient and remainder will be 1, 4, 1, 2, 0, 1, 0. So, we get the quotient which is less than the base. So, we will stop at this position. Now, from bottom to top, we can write the number is 1, 0, 0, 1, 1, 0, 0. So, this is the decimal 152 and its binary equivalent is 1, 0, 0, 1, 1, 0, 0. Next, we are going to convert a binary number into its equivalent decimal number. So, let us take the binary number is 1, 0, 0, 1, 1, 0, 0, 0. We have already learned that this is 152 in decimal. So, if we are able to convert this into its decimal, so we will get 152 and it will be a verification of our previous conversion also. Now, for this we have to put the binary bit into its position. So, this is the rightmost, so it will go to the position 0. Next 0, 0 and this one come to here. From right to left, we put the number from 0th position to the leftmost position, right? Rest of the 2 bit I can put 0 because there is nothing. Now, this power is actually base to the power position. Base to the power position and the weightage is the value of this one. So, 2 to the power 9 is actually 512. Similarly, 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, like this. 2 to the power 8 is 256 and 2 to the power 9 is 512. Next, what we have to do? We have to consider the position, we have to consider the weightages where the position have one value. So, and we have to add them up. So, we will go in, we have 128 plus 128 plus weightage is 16 plus 8, then all are zeros. So, 128 plus 16 is 144 plus 8 and it is 152, right? So, we have verified that this is 152 in decimal. Now, let's take an elaborate approach. Let's take another number. Suppose the number is, binary number is 1010 1 1 0 0. So what is actually we are doing? We are putting this 0 into 2 to the power 0 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus 1 into 2 to the power 3 plus 0 into 2 to the power 4 plus 1 into 2 to the power 5 plus 0 into 2 to the power 6 plus 1 into 2 to the power 7, right? So we'll get 128 plus 2 to the power 5 is 32 plus 2 to the power 3 is 8 plus 2 to the power 4, 2 to the power 2 is 4, and the rest of the part it will be 0. So we will get 160 plus 8, 168 plus 4, 172. Is that clear? So this is the binary equivalent, decimal equivalent of this binary number. Now let us use this table to do this one. So start from the right. So what we will get? The number is 0 0 1 1 0 1 0 1. What we have to do? We have to add the weightages. So 128 plus 32 plus 8 plus 4, and the rest of the part it will be 0. So 172. You can use this table, or you just have to remember the weightages and you can convert a binary number into its decimal number. Remember, we are discussing only the positive number, positive integer numbers. Now next we are going to discuss another way to convert a decimal number into its binary form. Now this process we are going to use the idea of subtraction and the weightages. So I have already write down the weightages. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7, 2 to the power 8, and 2 to the power 9. Now suppose we want to convert 114, which is in decimal, into its equivalent binary form. So 114 is obviously less than 128. Similarly, it is less than 512, 256. So I cannot take any of these three values from 114. So I have put 0 0 0. Now 64 is less than 114. So I can take 164 from this. So how much we have left? We have left with 50. Now can I take a 32? Yes, I can take a 32. So how much we have left? 18. Can I take a 16 from 18? Yes, I can. So I have left with 2. I cannot take a 8. I cannot take a 4, but I can take 1. So we have left with 0. Now, so we cannot take 1. Now add these weightages. So I will get 64 plus 32 plus 16 and plus 2. So 96 plus 16 is 112. So 104. So its binary equivalent will be 1110010. Is this clear? By subtracting, I can get the decimal binary equivalent of a decimal number. This process is much more easier to implement for a small decimal number, smaller decimal numbers. And if you remember these weightages and do some practice, it will be much more faster to convert a decimal into its binary using this method. Let us take another example. So the number here is 637 in decimal. So it is 100 more than 512. The next weightage is 1024. So 637 is less than 1024. So I cannot take 1034 or 24 from 637. But I can take 512 from 637. So we have left with 125. Now, can I take 256? No. Can I take 128? No. But I can take 64. So I have left with 61. I can take a 32. I have left with 29. I can take 16. I have left with 13. I can take 8. I have left with 5. I can take 4. I have left with 1. I cannot take a 2, but I can take 1. So finally we have left with nothing. So binary equivalent of 637 will be 0, that leading 0, 1, 0, 0, 1, 1, 1, 1, 1, and 0, 1. Right? So this is the binary equivalent of the decimal 637. By this method, if you do some practice and remember the weightages, you can easily convert any decimal number into its binary form in much more faster way than the quotient and the remainder method. In the next, we are going to discuss about the binary coded decimal or the BCD number. In this case, each of the decimal digit will be represented by its equivalent binary representation, and that equivalent binary representation will be of 4 bit. Now, this binary equivalent representation is also called BCD 8421 code. Why 8421? Remember, this 8421 are thus the weightages. So what are the digits we have? 0 to 9. So 0 will be represented by 4 zeros and 9 will be represented by 1 0 0 1. Now 8 4 2 1. This is the weightages. So 8 plus 1 9. Similarly 8 will be 1 0 0 0 and 7 will be 0 1 1 1. So you can find that 8421 using this conversion table. So digit 0 is 4 zeros and digit 9 is 1 0 0 1. Similarly, using this conversion table, we can convert any decimal number into its equivalent BCD number. Let us take, we have a number, BCD number, it is suppose say 29. So this is in decimal. Now each of the decimal digit will be converted into its BCD 8421 code. It is a 4-bit binary number. So 2 and 9. 9 will be 1 0 0 1 and 2 will be 0 0 1 0. So its BCD form will be 0 0 1 0 1 0 0 1. So it is in BCD. Remember, BCD and the binary is not same. BCD and binary is not same. BCD is binary coded decimal, and binary, if I convert it into its binary form, so it will be so you can clearly see that these two are not same, right? Now So do not confuse the BCD number with the binary number. Now here you have to mention the number system you are using. Without number system, mentioning the number system, this 10 may be 10 in decimal, but may be a 2 in in the binary number system also. So do not forget to mention the number system of the base you are using. Clear? Now for 0 to 9, a number ranging from 0 to 9, if we want to convert its binary to BCD value, we have to do nothing, right? Now for 0 from 10 to 19, for our integer value 10 to 19, if we want to convert its binary value into its BCD value, we have to add 6 to it. Similarly, 20 to 29, we have to add 12 to that number. From 30 to 39, we have to add 18 to that BCD number. As we haven't discussed the binary addition, we are not going to details of it, but remember this one. Next we are going to discuss the octal number system. Octal number system, the base is 8. It have 8 different octal digits, that is 0 to 7. 0 to 7 are the 8 different octal digits. Now to convert a decimal number into its equivalent octal number, we are going to use the quotient and the remainder method. Suppose we have a decimal number 123. Now this 123 need to be divided by the base. Here the base is 8. 123 by 8. So here the quotient is 15 and the remainder is 3. Now divide this 15, so that the quotient will be 1 and the remainder will be 7. Now the quotient is less than the base, so we can stop the division and we can write that it is 173 in octal. Right? Take another example. Suppose a small number 10. So 10 need to be divided by 8. We have a quotient of 1 and the remainder is 2. So it will be 1, 2 in octal. Suppose 50. So 50 will be divided by 8. Quotient will be 6, remainder will be 2. Quotient is less than the base, so it will be 62 in octal. Okay. Now the next is octal to decimal conversion. To octal to decimal conversion, we have to follow the process where we are going to implement the digit multiply summation of digit multiplied by the base to the power position, what we have done in case of binary numbers. So let us take 15 in octal. It will be 5 into base is 8, position is 0, plus 1 into base is 8, position is 1. So 8 plus 5, that is 13 in decimal. Similarly, one 137 in octal, it will be 7 into 8 to the power 0 plus 3 into 8 to the power 1 plus 1 into 8 square, that is 64 plus 24 plus 7. 64 plus 24 is 88 plus 7 is 95 in decimal. Is this clear? So this is how we are going to convert the octal number into its equivalent decimal number. Now next we are going to convert a octal number or binary number to octal number and octal number to binary number. To convert a octal or binary number to octal number, we have to group the consecutive 3 binary bit into 1, and this will give me 1 octal digit. We can use this conversion table. So octal digit 0 will be represented by 3 binary bits 000. Similarly, 7 will be represented by the binary bit 111, group of 3 binary bits. Now let us take example where we convert 1 1 0 1 0 1 this binary number into its equivalent octal number. So our number is 1 1 0 1 0 1. Group these 3 and these 3. This will give me 5 and this will give me 6. So it is 6 5 in octal. Remember, do not forget to write the base, otherwise the number will be different. Take another example. Suppose 1 1 1 1 1. This is in binary. Now we want to convert in octal. So 1 1 1 1 1. Now you can see that we cannot group them these 3, but there are no 3 bits. So put a leading 0 or pad it with a leading 0 so that we can make a group of 3. So this is one group, this is one group, and this is 7 and this is 3. So it is equivalent octal will be 3 7. Right? Now this is how we are going to convert a binary number into its equivalent octal number. Next we are going to convert an octal number into its equivalent binary number. Here what we have to do, each of the octal digit will be represented by a 3-bit binary equivalent using this conversion table. You can use this conversion table. So let us take 365. 365, this octal number we need to convert it into its binary value. So 365, each and every binary octal digit will be represented by its 3-bit binary equivalent. So it will be 101, 6 will be 110, and 3 will be 011. So finally we will get 011 110 101 in binary. Is this clear? So this is a very simple method. Using this conversion table you can convert any binary to octal and octal to binary number. Next we are going to discuss the hexadecimal number system. The hexadecimal number system, here the base is 16. So total 16 hexadecimal digits or symbols are available. Now hexadecimal 0 to 9 is same as decimal number, but from 10 to 15 the next of the rest 6 hexadecimal symbols of the digit will be represented by A to F, where A is equivalent to 10, B is equivalent to decimal 11, C is equivalent to decimal 12, D is equivalent to decimal 13, E is equivalent to decimal 14, and F is equivalent to decimal 15. So if we get 10 in decimal, it will be A in hexadecimal. Similarly, if we get 13 in decimal, it will be D in hexadecimal. So let us try to convert a decimal number into its equivalent hexadecimal form. Let's take a number. Suppose the number is 123. Divide and quotient method. Here the base is 16, so we have to divide the 123 by its base. So we will get a quotient of 7 and a remainder of 11, right? Now 11 is equivalent to B, we have already know that. So the hexadecimal number will be 7B, right? Suppose take another example, a smaller one, 20 in hexadecimal. So 20 divided by the base, the remainder, the quotient will be 1 and the remainder will be 4. So 1 and 4, base 16. Next we are going to convert a hexadecimal into its equivalent decimal form. So the formula is same. Digit summation of digit multiplied by the base to the power position. Summation of digit multiplied by base to the power position. So let us take 15 in base 16. So it will be 5 into 16 to the power 0 plus 1 into 16 to the power 1, that is 16 plus 5, 31 in decimal, right? Similarly, take another example, 137 in hexadecimal. So 7 into 16 to the power 0 plus 3 into 16 to the power 1 plus 1 into 16 square, that is 256 plus 48 plus 7. So 256 plus 14 is 304 plus 7, that is 311 in decimal, right? So this is how we can convert a hexadecimal number into its equivalent decimal form. Now to convert a binary to its equivalent hexadecimal form, we have to group 4 consecutive binary bit. This 4-bit consecutive binary bit is called a nibble. Now it will be converted to its equivalent hexadecimal digit. So 0 will be 4 zeros and F, that is 15, is 1111. So if you use the 8421, you can see that this is the 15 in decimal, so it is F. This is 14 in decimal, so it is E. This is 13 in decimal, so it is D. It is 12 in decimal, so it is C. This is 11 in decimal, so it is B. This is 10 in decimal, so it is A. And rest of the 9 digit will be represented by the 4 bit. So the converting to a hexadecimal number by binary number is very easy. Let us take an example. Suppose the number is 1101111 in binary. So what do we have to do? We have to make a group of 4 binary bit from right to left. So we can make this group, but there are no enough numbers of binary bit left. So we have to add with 2 zeros at the beginning. Yeah. So this is one group and this is one group. Is binary is 7 and it is 3. So this is 3 7 in hexadecimal number. Clear? Let us take another example. Suppose the number is 11101001001 in binary. So make a group of 4. This is one group, this is one group, and we do not have enough bit, so group it with pad with 0 at the leading end. So this is my 9, this is my 4, and this is my 7. So 749 in hexadecimal. Okay, that is how we are going to convert a binary into its equivalent hexadecimal form. Now next we are going to convert a hexadecimal number into its binary form using that conversion table. It will be much more easier. Each hexadecimal digit will be represented by its equivalent 4-bit binary form. So let us take, we have a number 4a in hexadecimal. So a is 1010 and 4 is 0100. So the number in binary, it will be 01001010. Yeah. Let us take another example. Suppose 3BCA in hexadecimal. So A will be, C will be 1100, B will be 1011, and 3 will be 0011. So the finally I will get 0011 1011 1100 0110. So this is the binary equivalent of this number. Converting hexadecimal to binary and the vice versa is very simple. You can use that conversion table. So a BCD number and a hexadecimal number, though both of them uses a 4-bit binary representation for each and every digit, but BCD digit will be from 0 to 9, so it cannot be greater than 9 for BCD number. But in case of hexadecimal number, it can be greater than 9. So 0 to 9 and from A to F are the hexadecimal digits, right? So do not confuse it between the BCD number and the hexadecimal number. Clear? So that's it for today's discussion. In the next video, we are going to cover the signed number representation, means how a negative number will be represented in a binary number system, then how to represent a floating point number and how it is actually stored in computer using IEEE 754 format, and then we are going to discuss the binary addition. That will be our part 2 of this topic. Now in the part 3, we are mainly going to focus on the subtraction, different kind of subtraction performed on the binary number system. Thank you and see you in the next lecture.